The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, I was at Atlanta yesterday and attending a conference. Met an expert from the disk drive industry. I know her well. And you remember I was just saying that the disk head and separation is below 10 nanometers. Do you know what's the separation now?
2?
That's say about 1.5 nanometers. That's what everybody has in a computer. It's amazing technology.
So we just go for solid state.
Huh?
We just go for solid state.
How much you can push, right? But this was actually a lab mate of mine, and she worked on nanoscale heat transfer, and they say that's a perfect place, because what they're doing is the magnetic, when you make it a very small domain, you actually cannot use a normal magnetic field to flip the magnetic domain, because otherwise at room temperature it just spontaneous flips back. So they have to use very hard magnet, and in that case they have to heat up the domain. So they have to heat up a nano domain first, and then apply magnetic field to write. So I thought I'll share this story with you. I'll talk a little bit more about that technology later on as we learn. So coming back to last lecture, what we talked is a reciprocal space. It's a continuation, and prove the Bragg condition, and that's the say when you do a transmission electron microscope or you do an X-ray, Bragg condition is the one when you look at diffraction patterns. And then we moved on to discuss the energy of the atomic vibration in crystals. And so we introduced the phonons, right? That's just the, say we solve the Newton's second law. So it's first is a continuum approach. It's a classical approach, but treating the atoms as discrete. And we got the dispersion between the vibrational frequency and the wave vector. And the wave vector is similarly, as in the case of electron, are discretized. If I have n atoms in the chain, and I have 2 pi over n, the separation is 2 pi over the length of the crystal. N times A is the length of the crystal, right? And we have acoustic branch. And if I have more than one atom at the lattice point, I have also optic branch. And the acoustic branch has longitudinal and transverse. Typically, longitudinal has a higher frequency, and transverse lower frequency. And in the case of optic phonon, this sometimes can cross over. So it's hard to say which one has a higher and lower. But I think if you deal with a polar crystal like sodium chloride, and you have always a transverse phonon lower and the longitudinal phonon, optical phonon higher frequency. So what's important later on is we'll simplify our models. And one way to simplify is the debye. So we treat this here. Although at the zone boundary, you can see we're careful in drawing this almost like a perpendicular. But say one approximation we use is approximate this by a straight line. That's the debye model. And the other is what original Einstein proposed, is just a constant frequency. That's an Einstein model. And you can see that Einstein model is closer for the optic phonons, or the debye model is closer for the, say, acoustic phonons. So that's where we were. And with that, if you recall what we have talked so far, very fast, right? We talked about energy levels, first in isolated atoms and molecules, and that's vibrational, translational, and electronic, rotational. And then we extend to crystals, and we say the treatment, the best treatment we've done is one dimension, and then we say, okay, if you look at the 3 dimension, each direction has a different periodicity and different potential, so your curve may look different, right? And with that, I hope you get appreciation for the energy levels of electrons in solid. With that, you can understand why there's an insulator, why there's semiconductor, why there are metals, right? And also, you can now also have some appreciation for the lattice vibration, the phonons, which is essentially here we do a classical treatment, but what phonon is a quantized form of this frequency. At each frequency, for that mode, you cannot have any energy. You can only have discrete number of phonon. The energy is quantized. Right. So those are this gives us some picture. What are the quantum mechanical allowable energy in matters? And where we're going to move is to add the temperature. This is a quantum mechanical allowable. Now, if I have an object at certain temperature, what's the statistically average, right? And what's the energy this object has? So that's where we're moving. And but before that, I want to discuss a little bit more of the counting, right? And if you recall, I said I emphasize degeneracy. A quantum state, right? Quantum state, right, is defined by, in the case of waves, if I have wave function, right? Let's say I have my wave function and kx, ky, kz. Right? Each of this kx, ky, kz. So here, for example, in one direction, I have discrete number of k values, right? Each combination of k value gives me one specific wave, a wave function, right? One wave function is, if I don't consider spin, right? Electron, I have to say one wave function because the wave function itself doesn't include spin. So that's one quantum state, okay? And in the case of discrete atoms, we say quantum numbers, right? If you recall, when we do electronic states, we have N, M, NLM, right? That's the quantum number. And we emphasize the because it's a different combination of NLM could actually have the same energy. That's where we say this is how you start to understand the periodic table, right? The degeneracy. Now, if you look at solid, I'm only drawing in one direction. But we know that the real crystal solid is 3 directions. And now, if I count certain frequency or certain energy, if you think about either frequency or energy, because H omega gives me energy, right? And even in the same direction, you can see here, I have 3 states, 3 wave vectors, right? That can have same quantum state, right? Same energy. So 3 wave vectors, 3 quantum states can have same energy. But if I look at the other directions, right, many other directions, I would have many other possible states that could have the same energy. So that's the degeneracy, and that's where I have to learn how to do that counting. Okay, so this is a major emphasis today. It's the idea of counting. Today we're really doing the density of states. And when I say states, I say this is like density of quantum states. Okay, and I also hope at the end I have, with that I'll get into quantum statistics. So this is my plan today. And let's start. We have looked at a very complex, say, band structure for electrons, for photons. This is like when to the Google and you look at all those different images, right? But say for the analytical purpose, we're going to look at the simplest model, like the Debye model. And for electrons, we also say if it's at the minimum of the conduction band or the maximum of the valence band, we expand that near that minimum maximum, right? So we have parabolic bands. So we need this. So if you recall for electrons, our approximation, and in the simplest picture, this is my K, and K you can think is Kx, Ky, Kz, and here is my conduction band, and I write this at the minimum K equals 0 minimum here, and you can put it at a different point, okay? And this curvature gives me effective mass. So if I say this is the energy and I expand this at the minimum, then the energy wave vector relation, right? And here is my EC, the bottom here. So energy wave vector relation is EC plus h bar k squared divided by 2 m star, right? So h bar k, we see under this effective mass concept, it's really just like the 1/2 mv squared, because the hk gives me momentum p divided by mass gives me gives me velocity, right? So that's the parabolic band approximation. And what we need to keep in mind, the k is a vector in 3D space, right? So kx, we said if in the x direction is 2 pi n times Lx, right? And again, at the end, if I do all this parabolic band approximation, my zoom boundary is here. This is a pi over ax, right? Nx is how many atoms times this period ax. Okay, so let's say Lx equals n in the x direction and periodicity in the x direction, right? That's our simple 1D model. Just to make a comment by passing, now some of you probably do work in graphene. See, what's special with graphene is that at the bottom here, the band here is not quite say a parabola. It's actually a straight line. Okay, so graphene, the dispersion, this is the energy. This is a wave vector. And in a small region near the Fermi level, right, it's a 0 gap. So the band gap happens to be 0. And so at the Fermi level, the dispersion is linear. And this linear dispersion makes it very similar to the Debye model for photon and also photon, right? Photon is, if you think about the model for photon, is omega equals ck, right? That's the speed of light. And for photon is omega equals vk. That v is the by velocity. Sometimes we associate with the sound velocity, right? So that makes the electron similar to photon and similar to phonons. So that's what's special with the graphene. This is kx, and of course I have similar k by kz, and the k square is a combination of kx square plus ky square plus kz square. Okay, so this means, right, my constant energy surface, if I give k is a constant, energy is a constant, right? Kx, ky, kz gives me a sphere. So it's a spherical, say, a constant energy surface. Sometimes if you draw a real constant energy surface in solid, it looks very complicated. Sometimes it looks like an ellipsoid or even other shapes. Okay? But I'm doing the simplest model. And so what you can say is there are many combinations of kx, ky, kz that could give me the same energy E. And each combination is one quantum state, including a factor of 2 if I think about spin. Right? So this is the dispersion, the energy with vector relation is dispersion, and for electrons. And for phonons, we already said omega equals Vk. That's the by approximation. And k, now that's the k for the electron, for the phonon wave vector. But again, based on discussion we have, those are allowable values, right? So and for photon, omega equals ck, like I just written down. But say this k for photon, I don't have a upper limit. I haven't discussed. So in free space, this k could be really large. Okay. So those are the dispersion between frequency wave vector or energy wave vector. All those we call dispersion relations, right? Now based on this, I'm going to count how many states. So it turns out, for example, I want to count, I have n electrons, right? Where is the Fermi level? If you recall when I did the simple one-dimensional hydrogen atomic chain, right? And we say this is the dispersion. Okay. And I have between here minus pi over a to plus pi over a symmetric, and I have k points. I say if it's in 1D, I go to the lowest states, and because I have n states between pi over a to minus pi over a to plus pi over a, I have n electrons, and each of these wave function have a spin up, spin down, so I fell to the middle, right? That's a 1D case. Now if I ask the same question, if it's a 3D, where does it go? Where is the filling? Right? And in that case, because there are many kx, ky, kz combination, k give me the same energy level, so I have to do this summation. So this is the total number of electrons. Let's say total number of atoms. Right? If I say hydrogen, each hydrogen give me 1 electron. Right? And then I have to sum up what I know is, let's say, at the 0 temperature, the lowest energy is filled first, right? So I have to think of this now rather than 1D, I have to think about 3D, 3-dimensional coordinate, right? And you will fill to the lowest and to the uppermost. This is recall. This is my EF. Right. That's where my Fermi level is. And correspondingly, this is my K. If I say this is my KF. Okay. And my model is X, Y, Z, all directions are the same. If you look at what I written down, right? So KF, so this is a constant energy sphere and the constant wave vector also at that location. So when they, so each of this combination Kx, Ky, Kz gives me one quantum state. As long as this quantum state lies below EF, it has one electron. So I add up that total should give me total number of n, total number of electrons. Okay, and recall this is a huge number, right? If I say one more, Avogadro constant 10 to the 23rd. Okay, it's going to be a very large number summation. So what I have here is going to, I say, Kx. So any of those allowable values below Kf, all that Kx value, right? I have many points there. I have Ky, same. I have Kz, right? As long as this Kx squared plus Ky squared plus Kz squared is within this is Kf squared, right? So as long as it's within this range, that combination, all those combinations give me a quantum state that's filled, right? So I have each Kx, Ky discrete points, Kx, Ky, Kz, gives me one quantum state except that doesn't count spin, so I have factor of 2, right? So each of this quantum state has one electron, right? 2 plus Kx, Ky, Kz combination has one electron, right? Each of this, so what I really sum up that one electron. Do you get me? I'm doing counting. It's basic counting. Okay? Now, if later on I'm not going to do 1, I'm going to do half filled at a certain temperature. For example, some states could be empty, right? So I may get, let's say, rather than 1, I may be a probability. We're very soon at the end of the lecture, I hope I get there. So this will be a function of energy and chemical potential and temperature, right? Here I'm doing my simplest case at 0 temperature. Any quantum state below the Fermi level are filled, and I have my requirement that I have total n electrons. And I want to find out where is my Kf, where is my Ef. Okay? So now you go to do the summation. How you do the summation, right? And doing summation when it has many, unless it's a simple series, it's not easy, right? So the way to do it is convert that summation into an integration. That's what we're going to do next. And the condition for converting a summation into integration, right? If I have a function here, right? And remember, this is a k. Each set of point is one value. I'm summing up those values when I do that summation, right? And now, if this function does not vary rapidly between the points, it's like you do trapezoidal rule. You can actually convert this sum back into integration. So how we do it? Okay, let's say Kx, right? If I have a delta Kx, right? right? Or dkx. When I do integration, I do dkx, right? So how many points there are in dkx? Now I look at the spacing between two adjacent points, kx, 2 pi n lx. So what's the spacing between two adjacent points? 2 pi over lx, right? So I do dkx divided by 2 pi lx. That's how many points over dkx? Okay, so now I'm converting this one, and rather than sum over say kx, I do integration over, this is my integration over kx. So what's my limit? If this is a kxf and minus kxf, right? So I have minus kfx plus kfx. Remember, I'm in symmetry, right? K negative, positive, k symmetric. Okay? And I do the same dky and 2 pi ly kfy kfy and kfz kfz dkz 2 pi lz. And that integration is over 1. But you probably don't like 1. 1 is just look too dull. So let me just put any function as I said before, right? Say later on when I say the Fermi level, I'll come back to f equals 1. So the f as a function of e mu t, right? And turns out this f could be any function. Sometimes this f could be a function of e. Sometimes this could be a function of k. Okay. And most of the time, when we do a deal with density of states, it's a function of e. So you want to convert a function of e or a function of frequency. But when you do transport, I just want to warn you, when you do transport, this function is often a function of k. So the way I do that, the summation sometimes in transport is actually not very useful. But it's such a so common concept that's used. Every time you go to read or you discuss, people say, what's your DOS? What's the density of states? Okay? So this is, I'm converting that. Of course, I have factor of 2. I have my n. This is the same. I'm writing that summation into integration. And so now with this, you can say Lx, Ly, Lz gives me volume, right? And 2 pi cubic. So what I have is 2 volume, 2 pi cubic. And then say I have, let me skip the integration limit. And what I have here is dkx, dky, dkz, right? Triple integral. So by this transformation, assuming this function f does not change very rapidly between adjacent points, I have converted this summation into integration. And now I have further freedom. Because you see here, if I give you this function f in terms of e is a function of k. So you have the freedom of how you do integration. Whether you integrate in terms of e or you integrate in terms of k, you have to relate them, right? Change into same variable so you can do your integration. And so what I can do is, here is what I'm doing is in a Cartesian coordinate, dkx, dky, dkz is a Cartesian coordinate, right? And if this is a spherical symmetric, so far, if it's a function of e, you can say if the function of e is spherical symmetric, right? I don't have, so if the function of e for Phonon here, omega is k. So it does not depend on, so in that case, it's much easier if I do convert kx, ky, kz into just k, into a spherical coordinate, right? Rather than doing triple integral, I do just say dk, dk, if it's doing spherical, if it's this one is not a function, it's only a function of absolute value of k. So this is a 4 pi. Can you tell me? Huh? K squared dk, right? Translating from a Cartesian into spherical. It's everything up here is math. But what's amazing is people, this is such a convenient concept to talk about, right? So here is 4 pi k squared dk. And then I can group this together. Okay. Now I'm going to group this back into here, so that I like to write n over v, but many people say so. This in that case, my density of states per unit volume. So here n over v then is the integration, and the f here I combine whatever all inside into, you can say I have pi square k square dk, right? And so here k is 0 to kf, 0 kf. Because I'm doing spherical coordinate, my radius is 0, my kf. I don't do negative positive because that's a Cartesian coordinate. You see what I'm doing? Okay? So this one now is my density of states. This is the density of states so it's the number of states per unit interval of k, right? How many states, quantum state I have per delta k, right? Because here I'm say in dk, my integration is in dk. So density of states in, if I write that as in terms of k, that means it's per delta k, okay? But say if you go back to what I alluded here, if my f is a function of e, then you have to make your choice whether you want to convert the e in this f into k, or you want to convert that dk into a function of e, right? It's just your choice. There's no formula there. It's whatever is mathematically convenient for you. So I could also convert, if I want to do convert into energy integration. So I will do EF and F. So in that case, I'll write this into k square pi square dk dE and dE, right? At the end, everything in this blob, I'm going to convert right in terms of E. So I have a relation between K, right, and E. So I can convert this K into E. So if I write this in terms of E, and I integrate over E, this is my density of states per energy interval, right? Here is my number of states per delta K. Here is my density of states per delta E. And say similarly, you can write your per delta omega, or per delta nu, or per delta lambda. So with that, I wanted just to say, you feel that it's a mathematical concept, and the K is you can translate. You can start from here. You can write your summation and go through that. I've done that probably hundreds of times, so now I can, I remember when I learned, I always go to the book and what's the formula given in the book. But if you get comfortable with that summation, it's translating summation into integration. And particularly when later on, when we do like a Boltzmann equation transport, this is going to be a function of kx, ky, kz. So I do not actually do, when I convert dkx, dky, dkz, I do theta phi, I do spherical coordinate, but I don't have the function itself, do not have spherical symmetry. So I will have to do, in the general case, this one, right? If I do spherical coordinate, is sine theta, d theta, d phi, d k, and k squared. So this will be my spherical converting a unit volume in Cartesian into a unit volume in spherical, right? But we're not doing the now. When you do transport, this is so common, okay? Okay, so that's the concept of density of states. And let's best use this concept and do a few examples to get familiar, more comfortable. So let's first look at the continuum Fermi level. Right? And I'm going to, you can take, in this case, it depends on where you take a reference, EC, right? Here, if I write the way I'm writing 0 to EF, integration is 0 to EF, means 0, the finite star, the E equals 0. So in that case, I cannot use EC. Because between 0 and the EC, there's no energy state. Electron cannot fill between 0 EC, right? So you have to be careful when you write those formulas and use yourself consistently. What's your reference, where you're doing your integration? Just a reminder. And if I do following what I have here, I have per unit volume, I give you this number of electrons. And I want to find that at the absolute 0 temperature, where is the uppermost energy level, right? So my band then, E equals h squared k squared 2m. Because my energy start, the finite start, this is my E, this is my K. I'm trying to find out where is EF, right? This is the Fermi level. And so in that case, what I have is F equals 1, right? That's below the Fermi level, all the energy, each state is spin up, spin down. So I have N equals NV equals 0 EF and 1. So the K square. So what's my K square? Now I need to convert. I want to convert it into E. Okay. This one is easy. That's my, if I do it in terms of K. But I want to do it in terms of E. And so what I have, K squared is 2m, right? So K equals 2m star E over h bar square 1/2, right? Based on the dispersion. So I have K squared is 2m star E h bar squared. That's my K square. Pi square. So I will put a pi square here. And then I have my dk dE. dk dE. This is my K. This is my E. So my dk dE is 1/2 2m star h bar square, and dk dE is this is 1/2, and E negative 1/2. So this is the overall integrate over dE. Now I'm going to erase this. So what I've written down is really what's inside this. I convert K into E. I convert dk dE, or write it also in terms of E, so that at the end I have all that blob is my dense substate. Right? So here is what's my dense substates. You say 2m h bar squared, that's 3/2. And so and the E minus 1/2. So my density of states is, I just want to check everything is written. It should be correct. Okay. So what I have here is 2 pi squared and m star 2m over h bar squared and 3/2 and E minus E 1/2. So this is my dense substate. And this E is referring to my 0 is at the bottom, EC. If I take my 0 at a different location, I have to do E minus EC. Okay? So if you, many times when I was just learning this, I just say, okay, I forgot it. I went back to the book, I do a derivation, and I plug in here. Because at the end, you want to do this F times dE and integrate over energy. But say, now I can comfortably sit there, and every time I forget, I say, I redo my summation to integration conversion. Okay, it takes many times. So that's the density of states, right? And of course, now I want to find out where is EF. Right? So here, if you say this is your EF, you put it in this density of states is dE dE, right? Essentially what I have here is 0 EF dE dE. Many times people get familiar. This is where they start. Right? I want to find out where is the EF, give me the number of electron. I write density of state, I integrate over E. That's how many states I have, right? Each state I have 1 electron, so that's how many electrons I have. And with that, you go to do your integration. You say this is a constant you can take out. It's really E half integration over E, dE, and to 0 to EF, right? So this will give you where is your Fermi level. You do your integration, you find out that your EF equals 3 pi square and 2/3 and h bar square 2m. That's after you do your integration and your inverse writing in terms of EF. Okay. Any question here? It's converting summation into integration. Do the correct counting. The density of states tells you the number of quantum state per energy interval, per wave vector interval, per frequency interval, many ways to write it. Okay? So it's electron. And just a comment, right? And let me draw the density of state for electron. This is the energy. This is dE, right? And if I have energy is relative to EC, this is E minus EC. So I put my EC not at 0, but at an arbitrary point. then this is the parabola density of state. That's the shape of density of state because it's square root. Okay, that's because if you see at the bottom, there are not many states, but you increase energy, there are a lot more states that have same energy values. Okay, so now let's do the same for Phonon. Conceptually, it follows the same process, converting the summation into integration. Okay, so I'm going to look at the Phonon. And I'm using the Debye model. And the Debye model say omega equals v times k, and this k is the magnitude of the wave vector, right? So it's the square root of kx squared plus ky squared plus kz squared. And also, in this case, the phonons are degenerate. 3 polarizations, transverse 2, longitudinal 1. And Debye just collapsed all the 3 into one line there. So, but you should still know there are 3 polarizations. Okay? So in that case, if you go back to starting from my summation, whatever function, right? And let's forget about what I'm going to integrate, because right now I don't have good stuff for f for you yet. We need to go to the say statistical distribution to say to actually give you f, for example, right? So I convert that summation into integration, same. But that factor of 2, which is spin for electron, need to become a factor of 3 because I have a polarization. The Debye model, I have 3 polarization, right? Okay. For each kx, ky, kz, I have 3 polarization. So I have 3. That's where my factor of 3. So if you look at my dk, that's where is my dk here? This is my density of state dk. Before it's a factor of 2, now it's a factor of 3, so that should be 3/2 of this. So my dk density of states for Phonon is 3/2. What I have here is a k squared pi squared. Right? Now my d omega is dk and dk d omega. So this is written eventually has to be changed into k has to be changed into omega. Right? Now I'm going to do frequency integration. Right? Phonon I normally don't do dE. My habit is typically do d omega. Now I do dk d omega. Right? So dk d omega, so dk is 3/2 k is omega over v here, square, pi square. And dk d omega is 1 over v. Right? Okay. So with that, I will get the 3/2 pi square v cubic omega square. So this is density of states for Phonon. And here is d omega, and here is omega. So it's the parabola. It's not square root. Density of states for electron is square root of energy, right? Here is actually square of energy. Okay. So different dispersion give you different density of states. Now, this could be easily converted into photon. Photon, no low longitudinal electromagnetic wave, right? Only two polarization, two transverse waves. Okay, and that two transverse waves should not be 3, it should be 2. And the speed of sound becomes speed of light, right? So for photon, density of state in terms of frequency is just omega square pi square c cubic. Okay. The best is so you sit there and write through all this, right? Getting yourself comfortable. It's mathematics. It's not much, really not much physics. Okay. So that's the case of 3D structure. Now let's do a 2D. I'm doing, okay, so we say, let's look at the quantum well. Let's look at thin film. What would be the quantization effect on the density of states? Okay, so let's do a 2D. I'm putting it here. This is the best place. I'm going to do a quantum well. Okay. Before, when we talk about quantum well, we say just a one-dimensional quantum well. Now I'm going to give you more realistic a film, right? In the case of film, electron can move in x, y, z, 3 dimension. And so if I have a film, and in the thickness direction I have Lz, okay? And in the xy direction, I have free motion. I don't have constraint, right? So my energy relation will be kx, ky. In the xy direction, I have discrete point as what we had before, but say that 2 pi Lx, 2 pi Ly, right? That's my separation. But my Lx, Ly in the xy direction are millimeters, or, right? That's macroscopic. So that separation is very small. On the z direction, I'm angstroms, 100 angstrom, right? So in that case, recall that when we discuss the energy in this direction is standing wave, right? So n, let me just use n, lambda over 2 equals Lz, right? And that means lambda equals Lz 2 divided by n, and you can convert this back into energy, right? HP, say the momentum k equals 2 pi over lambda, and what do you have here? 2 pi over lambda, lambda is there, so I have n pi over Lz, right? And the separation between, this is my k in the z direction. Separation is become pi over Lz. Now, if you look at the separation, we say in the unconstrained case, kx is 2 pi Lx over n, right? So in the unconstrained case, I have plus minus. And the separation is 2 pi over Lx. In the constrained case, I have n is only plus. Okay, and the separation is pi over Lz. It's a factor of 2 difference. That's because I'm using a traveling wave. This is a traveling wave, positive, negative direction, to construct a standing wave, right? So it's actually equivalent whether I use plus minus in the case or whether I use standing wave. But in the case of small length, Lz, I have to look at the separation because that summation cannot be converted into integration. So this is the difference. So if I write, in that case, I'll write my energy is h squared, say kx squared plus ky squared. That's in the, so effective mass in the implant direction, in the xy direction. Okay? And in the z direction, and I have, if I use this, I can do my energy quantization, right, is hk divided by hk squared divided by 2m. So 1/2 m hk squared, h squared, k squared is m pi over Lz squared, right? N equals 1, 2. Okay? So this is my energy level. I'm still writing h squared, kz squared. Now I do a standing wave. And because my Lz is very small, so between the two n consecutive n, there could be many kx, ky. Okay? So if you look at this, what I have here, recall in a 3D, right, a spherical, say we say a constant energy surface is a sphere, right? Now I have a constant energy surface, is the xy plane is a circle, but then depends on the n value, I have jumps, different values. Okay, depends on the different energy. So the other way to think about this, n equals 1. So this is where we draw quantization effect. This is the EC before. That's a bulk. Right? That's a bulk. Of course, I'm only drawing one direction. Okay? But you have to think of this as a kx, ky is like so you do a rotation. Right? So here, and when I have quantization, it turns out that the minimum energy now can no longer be here, because n equals 1, that gives me the first level. Right? So the bottom of the conduction band actually will shift up. Right? So that's why sometimes people say how I can open a gap. When I have quantization, I can artificially turn even a semi-metal into a semiconductor. Let me give you one idea. For example, when we work on thermoelectrics, there's a material bismuth. Turns out bismuth is like this, right? It's a semi-metal. There's no gap. This is the top of valence, bottom conduction. And conduction band is below valence band. So in this, the Fermi level is around here, and there's no gap. It's a semi-metal, right? Semi-metal is not good for thermoelectrics, and because when electron in this holes in this, they still have, you can still have electron holes, and when they diffuse to the same direction, the heat cancel each other. So it's not good. So how we can create a band gap out of this material? And you do a size effect, so you make it smaller. And theoretically, what happens is this one is a function of diameter or thickness. So this will move up, depending on thickness. This one will move down, right? So now you can create a gap. And there are also discussion, for example, in silicon, right? Silicon is like what you have here. This is it's an indirect gap. The valence band is here, conduction band is here, right? There is another conduction band, but it's not the minimum. This is the minimum. So now what do? You make a very small dots, and this will move up. Of course, this will move down. And this also depends on the speed of moving. That's related to the mass, right? And this could be moved to here, and this one moves slower. So this you can convert it into Dirac gap, right? So that's the beauty of this. Think about this quantum size effect. You can use that to tune the band gap of the materials. And that's when you make, say, like a quantum dots like cat telluride or cat sulfide, not cat telluride, cat sulfide, or if you look at the Professor Munji Bawenji's website, he has all these beautiful dots, different colors. And that's because the same material, you change the size, you can actually make a different gap. Okay? So those are digression. I'll come back to, I want to find out what's the dense substate, right? So let me again start with, okay, I have here is the number of electrons I gave to this, how many electrons in the material, and I still do my kx, ky, my kz, my f, whatever f I have there, function that I'm interested in integrating, right? And in 3D, I said this f is a very slow function of kx, ky, kz, so I convert it into integration. But in 2D, in the z direction, right, between two consecutive, so this is ESA, and my first energy level is here, my second energy level is here. Between these two, there are many kx, ky. There are many states in between kx, ky, right? So I cannot convert in the z direction into a summation, integration. I need to keep that summation. And what I could do is only convert the xy direction into integration. So this is what I'm going to do. I'm going to keep my, summation in the x direction. I can still do. So I have dkx, 2 pi lx. And y direction, I still do dky, 2 pi ly. And z direction, I cannot do. I'm going to keep my summation. And rather than kz, I can also do n. It's equivalent whether you do n notation or kz notation, right? And whatever f, I have a factor of 2. I move the inside, right? So now rather than do a 3D Cartesian coordinate, your mathematics is in 2D, kx, ky integration. So you do either a polar coordinate, or say it depends on your f. What's your f? F is a function of e, or is right? So that's your choice. But I'm going to do here. You say I have area Lx times Ly, and if I do dkx, dky, I convert it into a polar coordinate, right? Dkx, dky in a polar, if it's a symmetric, is 2 pi k dk, right? Let's say k, I just make a notation kx squared plus ky squared. So it's 2D, k parallel. So in this case, I have 2 pi k parallel dk parallel, and that's the dkx, dky, and then I have 2 pi square, that's here, 2 pi square. Then I have another 2 summation n f, right? You see, I'm not jumping into dense substate, I'm deriving dense substate. I'm comfortable doing that. Just converting the concept, just converting my summation into integration. And what I can do, right, if my f is the energy, so I can write my K parallel also in terms of energy. Right? So now like go back to the dispersion. Let's say this is this let me make a notation. This is my En, right? That's the sublevels of quantized in z direction, and this is my K parallel square. So I can write this my K parallel square equals 2m star h bar square E minus En. Right? So I have really, you can say here, I need to convert, if I want to write it in terms of dE, I need to convert this K parallel into energy. And I need to dK parallel dE. Okay? So if you do your math, if you go to look at what we have there, what I have is, so this is a 2 pi, cancel 1, and 2 cancel 1, I have another pi, right? So I have integration 1 over pi, and sigma whatever n f. And now I need to write here K parallel. In fact, if I put this in, I do the dk square, parallel square, because dk parallel square I have it here, right? So I have a dk parallel square. That means I have 1/2, I have 2m bar star, and h square and dE. I'm not sure whether you're following my conversion. I'm writing this into E. K parallel, D parallel based on what I have here. And of course, I have a summation n. That means when E has to be larger than En, right? Otherwise, this is say you can say if it's E is less than En, my K parallel will be imaginary. Okay. So what I have here, all this blob, lot of F is the one that I want to integrate. My density of states is this cancel, En, and m star, and h square, and I have another pi, and that's my density of state. Okay? It's a step function. N equals 1, n equals 2, you add another one, n equals 3, you add another one, right? So what I have here is, if I draw, this is my E, and say I have and this is my E1, E2, that's the quantization energy level, E3 is step function. And before we draw the electron, you go check your loads. This is the parabola, right? This is like a EC. That's the that's a 3D. This is 2D. So you see now that there are difference in density of states. And once you go to quantized mode, you got the more sharp features, right? Step function. And you go to wire, you got actually some delta function. The dots, you got delta function. It's this kind of step and delta or line that give you some very peculiar characteristics for the quantum systems. Okay? Any questions? It's math. Okay, it's a counting. No complicated physics. Yes, Vajra.
Your sum, your n is restricted, right? So you have.
Yeah. So the right way to write it is I write a Heaviside function. So Heaviside is a step function. Okay. Okay. So we spend most of today's lecture in doing the counting and say how I really is converting summation into integration. And if the function doesn't change much over the summation, I can convert. In the quantum's case, in the direction quantization, that conversion is usually have to be careful. You probably cannot do that conversion because there is a large change of that function in the summation direction. And what we're going next is do this F. Okay. In particular, we're doing a system at certain temperature, and what's the answer to the question at one quantum state, each quantum state, for example, what's the average number of electron? Because it could be 0 and 1, but at a certain temperature, there's a statistical average. What's that number? The same for photon, right? I can have 0, 1, infinite. Then what's the average number of photon for each quantum state? Now I know how I can count quantum state, right? How many quantum states I have. What I want to say next is at each quantum state, how many electrons, how many photons, given a certain temperature. Now I'm going to get into thermal system, right? And how much energy you have. So let me give a very say a beginning of that. And in fact, if you recall, we did in the first chapter we give you the Boltzmann factor, right? So this is my quantum statistics. And in the first chapter beginning, we say the Boltzmann factor gives you the probability of a particle. We were not discussing whether it's quantum or classical. Probability of a particle having certain energy at a certain temperature is a normalization factor minus, say, exponential e kBt. I said take it. This is the Boltzmann factor, right? You've seen many, say, examples of this Boltzmann factor. Say the energy barriers, Arrhenius law, all this is related to the Boltzmann factor. And next lecture, I hope I give you a little bit of rationale of this. Okay, there is a beautiful statistical framework to do that. So we use this, and then we went to the Maxwell distribution. Right? If I have a particle that has an energy 1/2 m Vx squared plus Vy squared plus Vz squared, right? I say, okay, I normalize this, I put it in here, and a particle has the probability between minus infinite to plus infinite is 1. So with that, I find that A, normalization factor. That's how I get the Maxwell distribution, right? So you see, in that process, I did not consider the discontinuity of the velocity, any value, between minus infinite to plus infinite. Now I'm going to do a little bit, say, discontinuous. Right? I'm going to ask you, for example, if I have a quantum state, electron is in thermal equilibrium with surrounding at a temperature T, right? And electron, say what's the average? So this is now I'm looking at the one quantum state, right? It's in thermal equilibrium with surrounding. I'm asking a question, what's the probability of this quantum state, how many electrons it has? Right? So that's the question I'm asking. And now the difference of that question, there are two differences compared to here. One is that electron in that quantum state, like it can go, the electron can be in that quantum state or jump out to the surrounding. So I have mass transfer, charge transfer, whatever, right? It's an open system. So that's 1. Second is that electron, that quantum state can only have 0 and 1, discrete. Okay? So when I have here, Boltzmann factor is for a closed system at constant temperature. And when I deal with an open system at a constant temperature, I have to modify this. So I'm going to give you again, just wait for the next lecture, say the Gibbs factor. And Gibbs factor is for open system. And the probability of a system, open system, has a certain energy and certain number of particles at a temperature T is A, again normalization, minus the energy of the system, minus the number of particles times this constant mu and divided by kBT. So now I add this mu, which is the chemical potential. That's to say how much energy you need to take out or place a particle into the system. That's the chemical potential. Okay? So mu is the chemical potential. And that's the same chemical potential is essentially the Gibbs free energy. And it doesn't include the entropy part, and the Gibbs free energy difference gives you how much work you can get out of the system. Okay, so with that, I'm considering one isolated electron, quantum state. This is the easiest. So I have one quantum state of electron, right? This is the solution you had before in quantum from either for solid or for molecule or for atom, right? You have the solution of quantum state. This is what we've been doing. The question is whether there is an electron in that quantum state or not. So what's the probability? Is it 0 or 1? Right? Say these are the two states. When n equals 0 or 1, when n equals 0, even though you have that quantum state, that state doesn't have real electron there, doesn't have energy. So the energy, when this is 0, this is 0. And when you have one particle, that energy, that state has energy EI. Right? So EI. Now I use this two possibility. I do my normalization factor for the Gibbs factor. So add up, it has to be either 0 or 1, right? The add up has to be 1. So when it's 0, P 0, 0 T plus P here is EI 1 T, that has to be 1. So the first one, 0, 0, that's just A. The second one, EI, so I have mass EI. Mu times N is just mu. KBT equals 1. So this gives me A equals exponential mass EI minus mu KBT plus 1. That's my normalization factor, A. Right? Now, my average number of particle, F, average number, which is the average number of N, right? Once I have distribution probability, I can find the average, any quantity, average energy, average number of particle, whatever average you want, right? So that should be 0, because 0 times this P 0, 0 T plus 1. I have 1 particle times P EI 1 T So that's my average number of particle, right? Because this is the probability when a EI1 fully empty. And you know your A, you know your P A times this, EI mu n. So you can say this one and this one is the same, right? In the numerator, I have this one. In the denominator, I have this one, but I have a plus factor 1, right? So I divide this so I can write this simpler. And you will see now what I have is EI minus mu KBT plus 1. And this is the famous fermi-dirac distribution. Okay, so in 3 steps, right? You get if you take that energy quantization, probability normalization, you get fermi-dirac. And the next lecture we'll go a few more steps to get the Bose-Einstein distribution for phonons. This is for electrons.